Welcome back, students, to this section of MCQs. Let us go further. Again, this looks like more on amino acids. So, protein chemistry and protein metabolism. The question is, an essential amino acid which is a precursor for the synthesis of a vitamin in the body. There are two things that are important here in this question. One, it should be an essential amino acid, and the second, it should be the precursor of a vitamin in the body. So let's look at it. The answer is tryptophan. Tryptophan, remember, by the kynurenine pathway is the precursor of tryptophan. Is the precursor by the kynurenine pathway. It forms 3-hydroxyantranilic acid, 3-hydroxykynurenine, kynurenine to 3-hydroxykynurenine, 3-hydroxy to 3-hydroxyantranilate, and etc. And it is a precursor of NAD. Vitamin coenzyme actually, rather than vitamin. It's more the NAD plus that is formed rather than the vitamin. So synthesis of a vitamin, more than saying the right word could be, right way to tell it could be synthesis of a vitamin coenzyme. NAD is a coenzyme form, but anyway we use it interchangingly many times. So effectively it has led to the formation of niacin, nicotinamide adenine dinucleotide. This vitamin is niacin. So tryptophan is a precursor for this. Next question. The protein electrophoretic pattern of a plasma sample reveals a fibrinogen peak within. There are two key points here. One, it is a plasma sample. What's the difference between serum and plasma? If blood is drawn into a plain tube and blood is allowed to clot, what will happen? The prothrombin fibrinogen blood clots. When blood clots, the fibrinogen levels will not be there in the when we centrifuge. What we get is serum, and this serum will not contain fibrinogen because it has already gone into the clot formation. Whereas if we add an anticoagulant and draw blood into it, what will happen? After some time the blood is not going to clot because you have added an anticoagulant, and plus when we centrifuge it, a clear fluid is got at the top where the RBCs settle down and we get a clear fluid at the top. This clear fluid which we get, we call it as plasma. That is the difference between serum and plasma. Now plasma contains fibrinogen. Why? It has not been clotted. Blood has not clotted. So fibrinogen is not used up. So when we subject plasma to electrophoresis, it will be different from the serum electrophoresis. So if you look at the electrophoretic pattern, always remember how electrophoresis is taking place. Serum, when it is subject, electrical movement is taking place. So if you put a slide, and this is the positive, this is the negative. The first band will be albumin, a thick band we get of albumin. It is all thick band. The next, if this is the origin, near the origin itself will be the gamma globulins, and in between will be the alpha band, alpha 2, beta. It goes like that. Albumin, alpha 1, alpha 2, beta, and gamma. And this will be the albumin. So albumin moves the fastest. Alpha 1, alpha 2, and beta and gamma. Now if you, instead of serum, if you do plasma, then what will happen? We'll get one more band in the gamma globulin region. And this band is because of fibrinogen. Now why we usually don't use plasma and we use serum is, we actually are looking for this, confuses with the M band. The M band position found in multiple myeloma is the same position. We will get fibrinogen peak also. So fibrinogen band and M band will overlap. So we cannot differentiate between multiple myeloma and ordinary normal person. So hence usually we do not use plasma. We always use serum. But in case plasma is used, fibrinogen will form a peak fibrinogen peak is seen within the gamma globulin region. So gamma globulins. Beta, albumin, alpha 1, alpha 2, no, because we start like this, albumin, alpha 1, alpha 2, beta, gamma. Now we are there, but in the gamma globulin region. So let's go to the next question. Positive nitrogen balance is seen in What is nitrogen balance? So what's your answer? If you have answered pregnancy, you have done a wonderful job. So what is nitrogen balance? Well, when is it positive? If protein synthesis is more than protein degradation, then you call it as positive nitrogen balance. When protein synthesis is more than protein degradation, you call it positive. Now rest all conditions. Starvation, is there protein degradation? Yes, proteins are used for gluconeogenesis and hence there will be protein degradation. The next choice was excess secretion of glucocorticoids. Glucocorticoids also lead to degradation of proteins. Protein degradation, especially muscle protein degradation, is caused by glucocorticoids. It is not an anabolic hormone, so it will cause protein degradation. It is a hyperglycemic hormone. Basically, it is to maintain the blood glucose level. Proteins, amino acids are degraded and it goes to the liver where it will help in gluconeogenesis. Old age, because of either the deficient intake of nitrogen, of proteins, or whatever reasons, there will be more of protein degradation. Pregnancy, yes, protein synthesis is more. So this is one of the conditions where we get positive nitrogen balance. Why? The fetus, for the development of fetus, protein synthesis has to take place. So protein synthesis will be more than protein degradation. Kwashiorkor, it is protein energy malnutrition. So naturally, protein degradation, protein in the diet is only not there. So it will lead to protein degradation. Proteins are going to be degraded. The muscle proteins are going to be degraded. So let's go to the next question. Tyrosine is a precursor for the formation of the following compounds except. So the answer should be, you should be knowing it, this serotonin. So remember, tyrosine, phenylalanine to tyrosine. Tyrosine is a precursor of catecholamines. Tyrosine is converted to dopa. Dopa is converted to dopamine. Dopamine is converted to adrenaline or epinephrine. Adrenaline is converted to, first it is converted to noradrenaline and then it is converted to adrenaline or epinephrine, adrenaline. So tyrosine to dopa, dopa to dopamine, dopamine to noradrenaline, noradrenaline to adrenaline. Here noradrenaline does not contain a methyl group, it undergoes methylation to form adrenaline, S-adenosine-methionine. So this is the pathway. So it forms dopamine, it forms epinephrine or adrenaline. Melanin, tyrosine is the precursor of the pigment melanin. Tyrosinase is the enzyme. Tyrosinase, it forms especially in the epidermal layer, skin cells. That is where melanin is formed. Eumelanin, chromelanin, there are different types of melanin, but the first enzyme is a copper containing enzyme, tyrosinase. Then serotonin is got from tryptophan and not from tyrosine. Thyroxine, yes, tyrosine residues, thyroglobulin, thyroxine residues are going to form. Tyrosine is going to get iodinated to form monoiodotyrosine, diiodotyrosine, which will then combine to form T3. MIT plus DIT forms T3. DIT plus DIT will form T4. T3 and T4 are the thyroid hormones. So thyroxine is T3. So tyrosine is the precursor of all of this except serotonin. Serotonin is got from tryptophan. Let's go to the next question. Biologically important compounds formed from glycine. We're looking at the whole of the amino acid metabolisms. So include all of the following except. So answer is GABA. GABA is got from glutamate. Glutamate is converted to GABA. It's a neurotransmitter. I think it is all should be known to you. GABA is an inhibitory neurotransmitter. So GABA is got from glutamate, whereas rest all of them are got from glycine. Glycine XY is the structure of collagen. Glycine XY is the structure of collagen. And if you look at heme, glycine plus succinyl CoA is responsible for the formation of the first step, delta amino levulinic acid. Glycine plus succinyl CoA in pyridoxal phosphate is required to form delta amino levulinic acid. The next was glutathione. Glutathione is gamma glutamyl cystinyl glycine. It is a tripeptide. So glutathione is also requires glycine. Creatine also requires glycine to form guanidocreatinine, which is further methylated to form creatine. So creatine, glutathione, heme, collagen, all of them require the formation of require glycine, except GABA, which is got from glutamate. So let's go to the next question. So this is somewhat similar to that of the previous one. Formed from tyrosine, include all of the following except thyroxine. I told you is got from tyrosine. So let's see what have we got. Melatonin. From where did melatonin come? Again, this is an example how the different compounds can be got. So again, tyrosine to dopa, dopa to dopamine, noradrenaline and epinephrine. So just a change of words. Adrenaline could be given or epinephrine could be given. Remember, adrenaline and epinephrine are the same. Melatonin is got from serotonin. Serotonin to N-acetyl serotonin to melatonin. So again, melatonin is something which is responsible for the biological clock, and it is got from tryptophan. It is synthesized in the pineal glands, and it is responsible for the biological clock, circadian rhythm, what we call a circadian rhythm, when to get up, when to sleep, when to feel hungry, when what has to take place, when to mature, when to get old or whatever, menarche, menopause, all these are because of melatonin. So melatonin is involved in different functions: seasonal variation, circadian rhythm, diurnal variation of different hormones, all different rhythms are supposed to be, biological clock is supposed to be because of melatonin. So it is got from tryptophan. So let's look at the next question. Hartnupp's disease, which is due to the defect in the intestinal and renal transport of neutral amino acids, leads to the deficiency of serine, glycine, tryptophan, tyrosine, alanine. The answer should be tryptophan. Remember, in Hartnupp's disease, tryptophan is deficient. Tryptophan is deficient means leads to deficiency of niacin or NAD. NAD deficiency means it will lead to that the pellagra. Niacin deficiency leads to pellagra. So the 3 Ds: diarrhea, dementia, dermatitis, all these 3, and finally death can happen in Hartnupp's disease. The pellagra-like symptoms can happen in due to deficiency of tryptophan. Carcinoid tumors also, there can be possibility of getting tryptophan deficiency, where tryptophan is used for the synthesis of serotonin. So Hartnupp's disease is due to both. All of the neutral amino acids also may be involved, but the most important one is tryptophan, which can lead to the deficiencies symptoms, because others can be synthesized within the body. This one cannot be synthesized. It is an essential amino acid, and thereby it leads to the deficiency symptoms of tryptophan, not of the other neutral amino acids. Let's go to the next question. Conversion of norepinephrine to epinephrine requires a SAM, PLP, TPP, methylcobalamin. Very nice question. All short forms. Let us look at it one by one. What was your answer? The answer should have been SAM. SAM stands for S-adenosyl methionine. S-adenosyl methionine. S-adenosyl methionine is a methyl group donor. Methionine is a methyl group donor. So what does it do? It gets converted to S-adenosyl homocysteine. It gives its methyl group to various acceptors. It gives its methyl group to various acceptors, and all the methyl groups to various acceptors form the methylated product. The enzymes are methyl transferases. So S-adenosyl methionine is converted to S-adenosyl homocysteine. In this, what is important? Norepinephrine is converted to epinephrine. So how do you remember? Norepinephrine does not contain methyl group. Okay, so that's how you remember. Norepinephrine has to be converted to epinephrine. So it will be norepinephrine is converted to epinephrine. S-adenosyl methionine is converted to S-adenosyl homocysteine. So what is happening in this? What are the other options? PAPS. What is PAPS? PAP is phosphoadenosine phosphosulfur. This is involved in sulfation of sulfolipids, etc. Wherever sulfur containing things are, sulfur metabolism is involved, PAPS is involved. It is got from cysteine. So not from methionine. Methionine to cysteine, cysteine to PAPS, sulfur metabolism. PLP is pyridoxal phosphate. It is vitamin B6 coenzyme. Pyridoxal phosphate, vitamin B6. It is not involved in this reaction, but further before that, before noradrenaline was synthesized, dopa to dopamine, PLP is required. TPP is thiamine pyrophosphate. Thiamine pyrophosphate is mainly involved in carbohydrate metabolism and not in amino acid metabolism. In amino acid metabolism, it is involved only in the branch chain amino acid metabolism. Rest all places, it is only 4 reactions within the body where TPP is involved, and that is pyruvate dehydrogenase, alpha ketoglutarate dehydrogenase, transketolase, and the branch chain amino acids. Methylcobalamin, again you might be wondering whether it is a methyl transferase, but no, methylcobalamin again only in 2 reactions within the body, and the methylcobalamin is mainly methylmalonate to succinyl-CoA, methylmalonyl-CoA to succinyl-CoA. That is where B12 is involved, where adenosyl B12 is involved, and homocysteine to methionine is where methylcobalamin is involved. Homocysteine to methionine, so not required for norepinephrine to epinephrine. We'll go ahead to the next question. All of the following statements regarding urea cycle are true except it takes place in the liver. It is partly mitochondrial, partly cytosolic. There is net production of 4 ATPase. It is regulated by N-acetyl glutamate. Urea is formed in the cytosol. So this is one of the questions by which you can know about the whole of the urea cycle, because most of them are true except. So the answer should have been, there is net production of 4 ATPase. Urea cycle, remember, is a catabolic pathway. Yes, true, it is a catabolic pathway, but it is a detoxification pathway also, where ammonia is getting detoxified to urea. So during this process, energy has to be put in. There should be an energy input, only then urea can be formed. So there is no net production of 4 ATPase, but there is actually net utilization of 4 ATPase. 4 ATPs are required to convert that ammonia into urea. So it takes place in the liver. Yes, it does take place only in the liver. It is partly mitochondrial and partly cytosolic. Yes, again it is carbamyl phosphate to forms with ornithine to form citrulline, and citrulline gets transported out of the mitochondria. Till that formation, till OTC formation, OTC enzyme, it is there in the mitochondria. Then again ornithine is retransported back. So it is partly mitochondrial and partly cytosolic. Yes, it is true. It is regulated by N-acetyl glutamate, and N-acetyl glutamate is one of the most important regulators of carbamyl phosphate synthetase 1. CPS1 is required in the first reaction, wherein ammonia combines with carbon dioxide to form carbamyl phosphate, and the enzyme is carbamyl phosphate synthetase 1, and this is requiring ATP, is converted to AMP, etc. Now what is important is this is positively regulated by N-acetyl glutamate. This N-acetyl glutamate, from where was it formed? It was formed from acetyl-CoA plus glutamate will form N-acetyl glutamate. So whenever in a well-fed state, glutamate is more, and that time all this will combine with acetyl-CoA, and this will spell N-acetyl glutamate, and this will stimulate CPS1, and more of ammonia is converted to urea. So in the well-fed state, more urea is formed because of the degradation. Whatever proteins are there, extra amino acids are never stored in the body. If there is more amino acids, they are just degraded to ammonia and urea. So it is regulated by N-acetyl glutamate levels. Again, glutamate is a transporter of ammonia. It indicates the ammonia status. So it will tell the liver enough ammonia is there, time to detoxify it, and it will be regulated. So urea is formed in the cytosol. Yes, arginase is the one enzyme which converts arginine, releases urea and forms ornithine. Ornithine enters back into the mitochondria. Let's go to the next question. The enzyme deficient in alkaptonuria is enzyme deficient in alkaptonuria. I think this is something that should be known, and the answer is homogentisate oxidase. Remember, from phenylalanine to tyrosine. Tyrosine metabolic pathway. Tyrosine is further converted to homogentic acid. Homogentic acid oxidase is responsible for the further conversion of homogentic acid to fumarate and acetoacetyl. So that's why it is both ketogenic and glucogenic. So the carbon skeleton tyrosine to homogentic acid is taking place. Now in this further metabolism, homogentic acid requires homogentic acid oxidase. This further metabolism is lost in alkaptonuria. Homogentic acid accumulates and this gets excreted in the urine, and this gets oxidized upon exposure to air, and this homogentic acid becomes black on standing. Homogentic acid also get deposited in different tissues, including the intervertebral discs, and this is known as ochronosis, wherein there is black deposition within the intervertebral discs and various cartilages, joints, etc. Most of the time these people are asymptomatic other than the black diaper syndrome, what is called as black diaper syndrome, but more debilitating is the arthritis that is caused because of the deposition of the alkaptone bodies in intervertebral discs or in the various arthritis joints, in various joints leading to arthritis. That is more debilitating for them. Overall, it doesn't cause so much of a problem. Rather, it is causing urine turns black upon standing because of conversion of homogentic acid is getting oxidized upon standing and forming what are called as alkaptone bodies, and that is why the name alkaptonuria for this. It is also called as a black diaper syndrome. So let's talk further about other MCQs in the further next section. Thank you.